Today we're talking about complex numbers and imaginary numbers, and first thing that we're going to talk about is just simplifying a square root of a negative number. So we have here an example, a square root of negative 28, and that is not possible to be square rooted in the real number system because a square root of a number means what number times itself gets you this, and you can't multiply two numbers times itself to get a negative. So what we have to do is break this down into negative 1 and positive 28. Now we can simplify the square root of 28, that's not too bad, but numbers that go into 28 are 14 and 2, and numbers into 14 are 2 and 7. Leaves me the prime factorization of this to be square root of negative 1 times 2 times 2 times 7. If you multiply all that out, you'll get to the negative 28 and you'll be just fine. Now remember what we did before. We want to simplify a square root. We look for pairs on the inside of the square root. In this case I have a pair of 2's, so I can pull that 2 on the outside. Now I could leave it as 2 times the square root of negative 7, but I don't really like that. That's not really nice because I didn't really take care of the negative thing. So what we have to do is talk about imaginary numbers. And the square root of a negative 1, even just one negative 1 by itself, is equal to I. Square root of negative 1 is equal to I. And I is just a symbol for an imaginary number. So we have this I that we get pulled out with the negative 1. The 2's go away, and then we have the 7 left on the inside. So the square root of negative 28 is 2I square root of 7. And that's as simple as it gets. Now, whenever we have a more complex problem with imaginary numbers, we look at this. We have to simplify, and we can either multiply the inside of the radicals first and then square root it, or what we can do is square root each side and then multiply and see if we can simplify after that. That is the advised option, especially if there's two negatives involved in the problem. I'll show you an example of that in just a second. So what I'm going to do is just simplify this part, then simplify this part, if I can, and then I'm going to multiply the stuff together. So now 2 and 3 are the only things that make 6, but I have to take care of the I. This is 3I root 6. Root 10 is 2 and 5. Can't really do anything with that, right? So it's going to just have to stay root 10. Now, I can multiply radicals together if they're the same radical, and if, the stuff inside, we can just multiply them together. So this is really 3I root 60. The important thing is that I take out any i's before I do this. Now, root 60 can be broken down into 2 times 3, which is the 6, and also the 2 times 5, which is the 10. We can just use the same numbers that we had for each individual root up there. 2 times 3 times 2 times 5. So this is 3I square root of 2, 2, 3, 5, all multiplied together. Now, of course, we have this pair of 2's that could come out, which would then be a 2 on the outside, which will get me a 6I root, and then 3 times 5 on the inside is 15. And that would be the final answer for this problem. Now, the problem comes when we have two negatives. A lot of people want to just go ahead and multiply these guys together right now and say that that is going to be the square root of a positive 200, and then break that down. Well, 200 is, 20 and 10, and 20 is equal to 4 and 5, and 4 is equal to 2 and 2, 5 is prime, and this is 2 and 5 as well. So then we could say the square root of 200, which is 2 times 2 times 2 times 5 times 5. And we can pull out pairs, and we get 2 and a 5 are the pairs. Now 2 times 5 is equal to 10, which is on the outside, root 2. And they would say this is the final answer, but that is not right. It's close, but it's not right, because of the way order of operations work. What the square root is really raising it to the negative, or to the 1/2 power. So this is negative 20 really raised to the 1/2 power. So it's not really shown that way, but that's what it is. And so that is an exponent. We need to calculate the exponent first, which means we have to square root the 20 and the 10 before we can do the multiplication of the two together. Order of operations still applies. So I'm going to have to pull out the I. Now I can simplify it completely down, or I can just say I root 20 times I root 10. And that would be fine. I could then have the positive 200 that comes out of here, but now I have an I squared in front of it. So I squared times root 200, which would be then I squared times, by the other math that we just did, 10 root 2. But the question is, what does this I squared mean? So I squared is I times I. And each I is the square root of negative 1 times the square root of negative 1. Now, whenever I write that, I could also write that as the square root of negative 1 squared. And when you square a square root, that'll simply get you a negative 1. I squared is negative 1. So this is negative, and then we have our 10 root 2. So it is just the sign error that you could get happening if you do not do it by order of operations. This is negative 10 root 2. Now, since I brought up the I squared and things like that, let's talk about the patterns of I. If you look at this number 11 here, it says I to the 5th power and asks you to simplify. And if that was an x to the 5th is simplified, you can't do that. But i's are not quite as easy. We know what I is. I is equal to I. We know what I squared is. We just calculated that. That was square root of negative 1 squared, which was equal to negative 1. Okay, so now we get to I cubed. We'll just go through and just figure out what I to the 5th is. I cubed. Well, logically, that would be I squared times I, because that's a total of 3 i's, right? And so therefore, that part, the I squared, is negative 1, and then we have the I, negative 1i. Well, now there's no power on that I anymore. And then we get to I to the 4th. Using the same argument as I cubed, we could say that was I squared, and then I squared again. Now I squared, we already figured out, was negative 1, and I squared again is again negative 1. Negative 1 times negative 1 is positive 1. Well, that's interesting. And then we get to our problem, I to the 5th. I to the 5th is equal to, well, we could write that using the same general logic as I to the 4th, and then one more I. But we already know I to the 4th, that's positive 1. So that is really saying that is 1 times I, which is, again, I. I to the 5th is equal to I. Now we can continue this pattern, so on and so forth. I to the 6th would be equal to I to the 4th, I squared. I to the 4th is just 1. 1 times anything is itself, so I to the 6th is equal to I squared, which is equal to negative 1, because we already calculated that up here. We can continue this pattern, but we'll realize that every 4 it repeats. So if I look at 17, we know that I is equal to I. We know that I squared is equal to negative 1. We know that I cubed is equal to negative 1i. And we know that I to the 4th is equal to positive 1. The 5th is equal to the 1st. The 6th is equal to the 2nd. The 7th is equal to the 3rd. And the 8th is equal to the 4th. Now I could keep writing them all out, following the same pattern over and over again. But I know that if it is 4, if there's a group of 4, that's equal to 1. So we could see how many times we could write I to the 17th out in groups of 4. Well, that would be I to the 4th times I to the 4th. That's the first 8 i's. Then another I to the 4th. Now we're at 12 i's. And then another I to the 4th. And now we're at 16 i's. And then we'd say I need one more to get to 17. Now I to the 4th we already calculated was 1. That is the key fact that we know right there. So this says 1 times 1 times 1 times 1 times I. And 1 times itself, well, obviously, doesn't matter. And so I to the 17th is also I. Now we can make it a little harder. Let's say this. Using powers of exponents, what we can do is we can multiply the two bases that are the same base, which means we'll add the exponents. So the 14 and the 23 would combine together to get I to the 37th power. And we will then calculate this out, and we'd say I to the 4th times I to the 4th times I to the 4th, and we just do a bunch of I to the 4ths until we get to the closest number to 37 that we can get. And that'll be the first 36 i's, because 4 goes into 36 even, leaving me one more to equal, again, just I. It's pure dumb luck that we've done 3 examples that give me I. But if we had I to the, say, 39th power instead, we'd still have to go to I to the 36, because that's 4 I to the 4th, or 9 I to the 4ths, and then we'd have 3 more i's. Now I to the 3rd we knew from the previous screen was equal to negative 1i, and that would be my answer for I to the 39th. So it could be any of the 4 options. Again, those 4 options are I is equal to obviously I squared is equal to negative 1, I cubed is equal to negative 1I, and I to the fourth, the important one, is equal to positive 1. Just repeating those patterns, it can be a little bit crazy. So we try to figure out what is the nearest power of 4 that is closest to the power that we want, in this case 36. Now, operations with complex numbers are not really all that complex. It's treated just like this had said, negative 2 minus 4x plus 7. All you do is simply combine your like terms. Negative 2, positive 7 combines to 5. Negative 4i doesn't have a like term, it can't combine. These ones are really simple. The more complicated ones are when it comes to multiplication. This is done just like a distributive property problem. Negative 4 times 8. Well, negative 4 times 8 is negative 32, but there is an I involved with that. And negative 4 times a negative 2i would be a positive 8, but we have the i's. I times I is I squared. But what was that I squared again from before? Well, we have a negative 32 plus 8 times I squared was negative 1. Well, 8 times negative 1 is minus 8, so this really says negative 8 minus 32i. I use the commutative property to switch the order around because I like to have my real number first before my imaginary number. Well, that's all well and good, but what if it's something more, I don't know, complicated, like that? And that is much more complicated, but it's not really. We have some multiplication that we have to take care of, and then we're going to add it to the other numbers, add and subtract. So let's go ahead and multiply. You can use the FOIL method, you can use the table method. 5 times 7 is 35. 5 times I is negative 5i. 4i times 7 is plus 28i. And then we get to the weird one, which is 4i times negative I, which is negative 4i squared. But I squared was what again? It was negative 1. Negative 4 times negative 1 is positive 4. And then we have the rest of our problem, a plus negative 6 plus 8i. Be careful with the negative sign, that is really plus 7 and plus I. Now we just have a really long problem that is not that difficult. We combine our like terms. We have all our I stuff that can combine together right there. So we'd say negative 5 and 28 is 23, plus another 8 is 31, and then plus another one is 32 i's. But we, of course, want to combine our numbers as well. 35 and positive 4 is 39, minus 6 is 33, plus 7 is 40. So we have 40 plus 32i as the answer to this problem.